So we have a name for function of functions. We call them functionals. For example, Ju is a functional which is a function of u and let's say its first derivative. It can also be a function of the second and third derivatives and so on. But let us restrict ourselves initially to a functional that depends on the function itself and on its first derivative. Not only that, we also restrict ourselves to functionals which are functions of a single dependent variable u, which is a function of a single independent variable. So we have a function of a single variable which depends on a single independent variable. And the only restriction that we have on this function is that at the endpoints, which are at x equal to a and x equal to b, it should have the specified values u0 and u1 respectively. Obviously, there can be infinite number of such functions. This is a function that is obviously satisfying this to essential boundary conditions, and all these functions, the infinite number of functions, will be called admissible functions. And now our task is to find the value of u. Let's say we call it the function yx, which is going to give the minimum value of this quantity. Remember, this quantity itself is a scalar, because once you have done this integration, what you get on the left hand side is a scalar. So yx is the function. If we replace u by yx, you get the minimum value of this scalar quantity ju. That is the yx that we are trying to find, and this is the way we will go about. Now let us assume that yx is this black function. And if you plug in this black function into this integral in place of u, you will get the minimum value of j. So let's say that's known. And then any other function u, any other admissible function u, can be constructed from y by a perturbation. So this perturbation is constructed by taking another function eta, which is 0 at a and b, and then multiplying by a small number epsilon. So y plus epsilon eta x will give you ux. You can take various forms of eta x and you will get various ux. The condition here would be that all these ux's will be admissible. So this is the function that actually minimizes, and this is a perturbation on that function. So the red function is constructed by multiplying the the cyan colored function, which is 0 at the ends, by a small number epsilon, and adding it to the actual function yx, which we still do not know. Okay, so now my condition here now becomes that eta a, this cyan function, should be 0 at a and b, where essential boundary conditions are satisfied. If I do that, then ux will of course be admissible. Now I can plug this into ju, the functional. I can plug this in. So in place of u, I have y plus epsilon eta, and in place of this is u, and this is u prime. Okay, and now let us call this whole thing now is a function of eta, function of epsilon. Eta is an arbitrary function, so this whole thing is a function of epsilon, and let's call that function phi epsilon, and this will be a minimum when d phi epsilon will be equal to 0. So the problem of finding y has been reduced to a problem of finding a value of epsilon that minimizes phi e. So this is actually an identity. So what we have written here is that d epsilon of phi e has to be equal to 0 for this to be a minimum. But then we know that this is a minimum when epsilon equal to 0. So we know the result of this, that when epsilon equal to 0, this will be equal to 0. So we know at the minimum this will be equal to 0, but we know where the minimum is. The minimum is at epsilon equal to 0. So this identity has to be valid. So please stop here for a moment and think about this statement. All that I have written is that is an identity which is always correct. So this identity has to be handled in order to find out this unknown function yx, which minimizes j of u. So we know that when epsilon equal to 0, I have made a mistake here. This would be y. This would be y. I'm sorry. So when epsilon equal to 0, this would be a minimum and its value would be equal to 0. When epsilon equal to 0, this quantity would be a minimum, and therefore del epsilon of that will be equal to 0. Now we will calculate this quantity from here. To do that, let us look at the integrand, and let us try to calculate del phi d epsilon. So this is what we are trying to calculate, and d phi d epsilon is integral a to b of d epsilon of f, which is a function of x, u, and u prime. So we can apply partial chain rule here. So we get a to b del f del u du d epsilon plus del f del u prime d u prime del epsilon dx, and du d epsilon, from here du d epsilon is eta and du prime d epsilon is eta prime. So we can write this as a to b del f del u eta plus del f del u prime eta prime dx. Now look at this second integral, which is, let me rub some things. So let us look at this one, del f del u prime eta prime dx. I want to get rid of this eta prime, so I do integration by parts. So that will give me, the first term would be, this is a to b, and the first term would be, let's keep del f del u prime as it is, and eta prime derivative is eta from a to b minus of integral a to b. I have to take integral of this, or I have to take derivative of this. So d dx of del f del u prime, and integrate this, that will give me eta dx. So this is the second integral. Therefore the total thing I can write as a to b f u, indicating del f del u, minus d dx of f u prime eta dx plus del f u prime eta evaluated at a and b. So value of eta at a and b are equal to 0. Value of eta at a and b are equal to 0. So this is all that I am left with. So that is what I have done here, and I know that d epsilon of j y plus epsilon eta, that is u, at epsilon equal to 0 is equal to 0 is my identity. So I calculate this quantity at epsilon equal to 0, and this is what I'll get. because all the epsilons will go to 0, all the epsilons here will go to 0, and this is what I will be left with. This will be 0 because eta is equal to 0 at both a and b. And when you look at this, you have to consider the fact that eta is an arbitrary function. I have not put any restriction on eta except that it is 0 at a and b, and since eta is an arbitrary function and this has to be always true, this always has to be true no matter what the value of epsilon is. If this has always to be true for any value of eta, then the quantity inside the square brackets has to be equal to 0 all the time. That will only ensure that this can never be violated, and therefore this is the equation that I use. This is the equation that I use to find out y. So this is a differential equation, and this differential equation can be solved to find out y. So what I have shown here is you can take this differential equation, which by the way is known as the famous Euler Lagrange equation. You can take this differential equation and solve for y. The solution that you will get for the given essential boundary conditions, the solution that you will get is the same solution that you will get by minimizing this functional. So from every functional, we can build a differential equation. Solving the differential equation, minimizing the functional, will lead you to the same result as long as the essential boundary conditions are satisfied. Okay, so this is the idea of variational calculus. We'll see one or two examples. So let's look at the Euler Lagrange equation a little carefully. So what you have here is del f del y minus ddx of del f del y prime equal to 0. This is your Euler Lagrange equation for a functional of a single dependent variable of a single independent variable. So okay, so now here's a problem, simple problem. So this is your functional, this is your f, and it is f of u is u prime square minus u square. So calculate del f del u, that is minus 2u. Calculate del f del u prime, that is 2u prime. Calculate ddx, this is a function of one variable only. So calculate ddx of del f del u prime, which will be 2 into ddx of u prime, that is 2u double prime. So your Euler Lagrange equation is del f del u minus ddx of del f del u prime, which will give you minus 2u minus 2u double dashed equal to 0. So your differential equation corresponding to the minimization of this function is simply u double prime plus u equal to 0 with the boundary conditions, with the essential boundary conditions u0 equal to 0 and u pi by 2 equal to 1. You can easily solve this second order differential equation, put these boundary conditions and find that the function that minimizes I is simply y equal to sine x. So the minimum value of this quantity I will be obtained when you take u equal to sine x and do this integration. When you do that, the value of this will be a minimum. That's what is equivalent to solving this differential equation. So this is one example, and we will look at other examples in the next installment.